Hello, welcome to another session on this series on maths for data sciences. So in the previous session, we looked at what are discrete distributions. These are basically distributions where the random variable x can only take some limited finite values of x. So there are only countable values of x that the random variable can take. Those distributions are called discrete distributions. Then we looked at three of these distributions. The first being uniform distribution, which as the name suggests, it is distribution where all the values of x takes the probabilities which are equal in value. So for example, if we have a uniform distribution which is represented as u1, 2 and 3 in curly braces, this means that this distribution can only take values 1, 2 and 3. So only 3 possible values are there, and the probability of each one of them, since they are equal, uniform, therefore the probability should be 1 by 3 for each of these values of x. Then we looked at binomial distribution, which basically represents the number of events that happen in n trials, given that the probability of an event happening in each of the n trials is equal to p. So P is the probability of success or probability of an event to occur in each of the n trials. Finally, we looked at Bernoulli distribution, which is nothing but a special case of binomial distribution with n equal to 1. Therefore, there is only one trial, and thus in this case, since theta is the parameter here, we write Px equal to 0 as 1 minus theta and Px equal to 1 as theta. So this is a probability mass function for a Bernoulli distribution with parameter theta. Now one more thing we wanted to mention about binomial distribution, which we have mentioned, but to make things more organized, we want to look at the 4 assumptions. So these are some important assumptions which we made when we were describing a binomial distribution. The first one being there are fixed number of trials. So obviously, like, this is actually the first parameter of the distribution itself, which is n. The number of trials for a binomial distribution should be fixed, which is equal to n. All the n trials should be dichotomous, which means this term here means only 2 possible outcomes. So just like we saw the example in our previous session, whether it will rain or not on a particular day. So there are only 2 possible outcomes for each of the trial. This is rain or no rain. Therefore, all the trials, all the n trials should be dichotomous, which means each one of them can only have these 2 possible outcomes. Then the probability of event happening, this is sometimes also called the probability of success. So the probability of event happening should be equal for each of the n trials. So for each of the n trials, the probability should be equal, which is equal to the second parameter here, that is the value of p. Then the fourth assumption is all the n trials should be independent of each other. Now this is very important here because like we saw, the rule of independence says that the probability of occurrence of an event in a particular trial, let's say trial number 3, is independent of whether the trial has happened or whether the event has happened in any other trial or not. So the result of any other trial would not affect the result of any other trial. So if you are considering, let's say, trial 3, the probability of success is p. It is independent of any other trial or the result of any other trial. The probability still remains p. So these are the 4 major assumptions of a binomial distribution. And these are sometimes important because these are have been asked in some of the interviews which are taken for a data sciences role. Now that we have covered these three distributions, we would cover a couple of more discrete distributions. So the first one of them being a geometric distribution. So a geometric distribution is the number of trials required to get the first success. So for example, let us say we toss a coin until we get a heads. Now the number of trials required to get the first head would be a geometric distribution. Now, for example, to get the first head, let us say we look at all the possible scenarios when we can get the first head. So let us say we get it on the first trial itself. Now, in this case, the value of the random variable would be 1, since there was only one trial required to get the required outcome, which is head. Now, let us say we get the first toss result as tails. So we need to continue since we have not got a head, and then we get a head. So the x value here is 2. Now similarly, let us say we have got 4 tails and then we got a head. So in this case, the value of x is equal to 5. So this is how we define a geometric distribution. Now to get the probability mass function of this particular distribution, I think till now one should be able to get the probability mass function on their own, but I'll be anyways going through it anyways. So let us say we want to calculate the probability of the random variable x taking a value of x. What do we need? We need probability of no success in x minus 1 trials multiplied by probability of success in the xth trial. So this is because if there is no success in the first x minus 1 trials, we'll still go on to find the first success, and if we get it on the xth trial, we'll stop at that moment. Now the probability of no success in the first x minus 1 trials is what? 1 minus p raised to power x minus 1, where p is the probability of success in each of the trials multiplied by p, which is the probability of success in the xth trial. So this is the geometric distribution probability mass function, and now we can easily get the probabilities here for different values of x, which we saw earlier. So for x equal to 1, it will be p, since there's a p probability of getting a head in the first toss. Then for getting first tail and then head, it should be 1 minus p into p, and then 4 tails and 1 head, it should be 1 minus p raised to power 4 multiplied by 1 p, because that is the probability of ultimately getting a head. So this is how we get the probability distribution for a geometric distribution. So this is about the geometric distribution. Now moving on, we'll be moving to our fifth distribution, which is a Poisson distribution. So in this case, let us say there's a crossway, and there are a lot of cars. So let us say C1, C2. These cars keeps on crossing the crossway, and the one thing to mention in the geometric distribution is geometric distribution could be written as geometric P, where P is the parameter here. So there's only one parameter here, just like the Bernoulli distribution where we had only one parameter, which was the probability parameter. Here also we have one parameter, which is the probability parameter. And also it is the difference between geometric and binomial distribution, as you can already see, would be the number of trials required to get the first success is not fixed in geometric distribution, while the total number of trials in case of binomial distribution was fixed. And then in binomial distribution, we were actually looking at the total number of successes in n trials. But here there will be only one success for which we are waiting for. And once we get the first success, we stop. So these are the major differences between the two distributions. Now coming back to Poisson distribution, here we were looking at the example of cars crossing the crossway and the parameter here. So we denote it by lambda, and this denotes the average number of arrivals per unit time. Now an important assumption here: arrivals are independent of each other. So just like we had the assumption of independence in binomial distribution, here we also assume that arrivals are independent of each other. Also, rate of arrival, which is lambda. So rate of arrival is same as the average number of arrivals per unit time, is same across all time periods. Now the probability mass function for Poisson distribution is given as P x equal to x lambda to the power x e to the power minus lambda divided by x factorial. Now, like we were able to intuitively derive the probability mass functions for binomial distribution as well as geometric distribution, we don't need to worry about that. In case of Poisson distribution, it would be better to just remember this particular formula. And this is actually this particular distribution is actually used in a lot of statistical applications. One of them being the Q theory, where the rate of arrivals are actually modeled. The arrival process itself is modeled using a Poisson process very often. So this is about the Poisson distribution, and this distribution is used to get the. So the random variable x here is defined as total number of arrivals in time 1. So, or per unit time. Now let us say we have a total time given as t. So instead of per unit time, we want to get the total number of arrivals in time t. So what do? Since the average number of arrivals, so average number of arrivals per unit time is lambda, then average number of arrivals in time t would be lambda times t. Therefore, we just replace lambda with lambda t. So we call this xt, let us say, and we replace lambda with lambda t. So since the new arrival rate becomes lambda t for a total time of t, therefore the total number of arrivals in time t could be modeled using this particular probability mass function here. Now there could be some values that could be derived here. So pxt equal to, let us say, 0, this is given as, so this 0, the first power lambda t would become 0, so this will become 1, and e to the power minus lambda t divided by 0 factorial, so 0 factorial is again 1, this becomes e to the power minus lambda t. Now, since this random variable x is defined as the total number of arrivals in a particular time period, it obviously cannot be negative. So it can only take non-negative values and integer values. So the possible values of x that it can take are x, 0, 1, 2, 3, and so on till infinity. Similarly, the total, the value for geometric random variable could be equal to 1, 2, 3, and infinity. So once again, here in geometric variable distribution, we cannot have a variable of 0 because obviously we need at least one trial to get the first success. So it starts with the minimum value of 1. But in case of Poisson distribution, since there could be 0 arrivals, therefore we start the value of this random variable with 0, but it can go up to as high as possible. And both geometric and Poisson distribution can only take integer values. So this is about Poisson and the geometric distribution. So in the next session, we'll look at some of the properties of these discrete distributions which we have seen. So we are going to derive the expected values and variances. So that will give an introduction to new concepts as well. And we'll derive these concepts for the various distributions which we have seen.